In this video, we're going to be looking at one of the major topics in calculus. The first major topic was derivatives, and our second major topic is antiderivatives. And an antiderivative is just as it sounds. If you find the derivative of some function, for instance, if I find the derivative of, let's say, the sine function, we know the derivative of sine is cosine. What we're going to be looking at in this section is if we were given the cosine and asked for the antiderivative of cosine, we would just be reversing this process. Since this is considered now the derivative, this now, the sine, would be considered the antiderivative of cosine. So it's just the reversing process of finding a derivative. We're going to have some function. If we took the derivative of some function, it would give us this. And so what would the antiderivative of cosine be? Well, the antiderivative would be sine. So that's the idea behind an antiderivative. Now there's a lot of applications for this that we'll get into later. Here's a definition. A function f, capital F, is called an antiderivative of lowercase f on an interval I if f prime of x equals f of x for all x in the interval. Now this should make sense because if capital F is the antiderivative, if we take the derivative of an antiderivative, we should get the original function back. So for instance, if we have f of x equals x squared, if f is the derivative of some function, what was the original function? Well, one function may be 1/3 x cubed, because if we take the derivative of 1/3 x cubed, we get x squared. Another may be 1/3 x cubed minus 50, because if we take the derivative of 1/3 x cubed minus 50, we also get x squared. We could even say 1/3 x cubed plus 4, because h prime of x also would give us x squared. So you can see we would have an infinite number of antiderivatives. So to indicate that we could have any other constant on the end, we just indicate that as plus c. If f is an antiderivative of f on an interval I, then the most general antiderivative of f on I is capital F of x plus c, where c is just some arbitrary constant. Because if we were to check if this is the correct antiderivative by taking the derivative, that constant would just go to 0. Now, if we were to graph the antiderivative of the function that we were looking at, our f of x equals x squared. Now, graphing the antiderivative, since we would get 1/3 x cubed plus some constant, we would get what's called a family of curves. And I've just drawn in a few of them here. We would have an infinite number of curves because C could take on any value. Find the most general antiderivative of each of the following functions. Part A. If we're thinking that the derivative of some function gave us sine of x, what would that function have been that gives us sine of x? If we take the derivative of some function, we get sine of x. So we may be thinking, if we took the derivative of negative cosine of x, we would get the sine of x. So the antiderivative of the sine of x is negative cosine of x plus some constant of integration. Part B, let's think about this the same way. If we took the derivative of some function and got 1 over x, what would this function be that we took the derivative of to get 1 over x? And we're thinking, well, if we get 1 over x, we took the derivative of ln of x. So the antiderivative of 1 over x would be ln of x plus c. And we're going to look at the reason why, but the actual antiderivative would be the natural log of the absolute value of x. Part C. Here we're going to generalize now. If we take the function x to the n, where n does not equal negative 1, what would be the antiderivative? Well, if we looked at a few more examples, what would the antiderivative of x squared be? Well, if we thought about this, and I think we saw that on the last slide, one antiderivative would be x cubed over 3. Because if we take the derivative of x cubed over 3, we get x cubed. What is the antiderivative of x cubed? If we take the derivative of x to the 4th divided by 4, we would get x cubed. If we looked at what's the antiderivative of x to the 4th, we would see that if we take the derivative of x to the 5th over 5, we would get x to the 4th. So if we generalized this and asked what's the antiderivative of x to the n, we would say x to the n plus 1 all divided by n plus 1 plus some constant of integration. Now it says n cannot equal negative 1. Well, if n equals negative 1, this is the same as 1 over x, and we saw the antiderivative of 1 over x is ln of x. Here is a table of anti-differentiation formulas. We should know these by thinking about the process of, if I take the derivative of some function and get what's listed in this first column, what function did I take the derivative of to get this? So if you thought these through, you should be able to come up with the particular antiderivative. Now on these, I don't write plus c because we're saying this is a particular antiderivative, and the particular value of c that I'm giving these antiderivatives is 0. So I'm just saying ln of x plus 0, e to the x plus 0, sine of x plus 0. So this is a particular antiderivative where c equals 0 in the case from the third function down. So those are some antiderivatives we should know and be familiar with at this point. Find all functions g such that g prime of x equals, we have 4 sine of x minus 3x to the fifth plus 6 times the fourth root of x cubed. First of all, let's write this as g prime of x equals 4 times the sine of x minus 3x to the fifth plus 6 times x to the 3/4 power. Now from the last slide, we know that if we take the antiderivative of 4 times the sine of x, we can take the derivative, we can take the antiderivative of the sine of x and then multiply it by its constant, 4. So the antiderivative of the sine of x is negative cosine of x. With the second term, same idea. We're going to find the antiderivative of x to the fifth and then multiply it by 3. Well, the general rule we saw, we would add 1 to the exponent and then divide by that same power. So there's the antiderivative of 3x to the fifth. For the last term, we're going to find the antiderivative of x to the 3/4. Now we need to add 1 to the exponent. What I like to do is I like to just get a common denominator. There's adding 1 to that exponent, which gives me x to the 7/4. And then we divide by that same power. And then we could add our constant of integration. If we simplified this a little bit, we'd get negative 4 times cosine of x. And we can reduce here. So we'd have x to the 6th over 2 plus, now this right here, this 7/4 in the denominator, we can invert and multiply. So when we invert and multiply, it becomes 4 divided by 7. So we would have 24 divided by 7 times x to the 7/4 plus our c. And let me explain what happened up here. We had 6 times x to the 7/4, and we said we're going to take this and invert and multiply. So if we invert and multiply, this becomes 4 over 7. And you can see we'll multiply 6 times 4 divided by the 7, x to the 7/4. An equation that involves the derivatives of a function is called a differential equation. Now, there is a class in college that you may take. It's called differential equations, or for short, diff EQ, which comes from this here, diff EQ. So in college, you'll hear some students talking about a class called diff EQ, which is just differential equations. Here's an example of a differential equation. This is an equation that involves the derivatives of a function. So we have f prime of x equals e to the x plus 20 times 1 plus x squared to the negative 1. It also gives us what's called an initial condition. F of 0 equals negative 2. Now that's going to help us solve for that constant of integration, because remember, when we find the solution or an antiderivative, we get a constant of integration. If we have what's called an initial condition, we're able to find that constant of integration. So this is our initial condition. This right here. And that will help us find our constant of integration. Now, in this example, it says find f. Well, what's given is f prime of x. So we are actually trying to find the antiderivative of this function. So let's look at each term. Actually, let's go ahead and just rewrite this before we get started. This is e to the x plus 20 times, I'm going to rewrite this as 1 all over 1 plus x squared. Now we're going to find the antiderivative of each term. The antiderivative of e to the x is e to the x, because if we take the derivative of e to the x, it's just e to the x plus 20 times. Now the antiderivative of 1 divided by 1 plus x squared is tangent inverse of x. If we take the derivative of tangent inverse of x, we get 1 all over 1 plus x squared. And then we have our constant of integration. So there's our function f. Now it gives us an initial condition. It says f of 0 equals negative 2, which means if I plug in 0 for all my x's, f of 0 equals negative 2. So let's see if we can solve for our constant of integration. So we would have negative 2 equals e to the 0 plus 20 times the tangent inverse of 0 plus c. So we would get e to the 0 is 1 plus 20 times tangent inverse of 0 is 0. So we have, this goes to 0. So if we subtract 1 from both sides, we get negative 3 equals c. So with our initial condition, we're able to find a particular solution. If we're given an initial condition, we can find the particular solution. That just means we can solve for c. So our function would be e to the x plus 20 times tangent inverse of x minus 3. That's our particular solution, because we were given an initial condition. We can find our particular solution. Here's another example. Find f if f double prime of x equals 12x squared plus 6x minus 4. And again, we have initial conditions, so we should be able to find a particular solution. First off, we should be able to find f prime of x by finding the antiderivative of f double prime. That would give us f prime of x. So let's apply the rules. Here we would add 1 to the exponent and divide by that same power, plus 6 times, now here the power is just 1, so we would add 1 to the exponent and divide by that same power. Now think about 4 as 4x to the 0 power. If we add 1 to the exponent, we get x to the first all divided by 1. So if we clean that up a little bit, we'd have 4x cubed plus 3x squared minus 4x plus c. That's our f prime of x. To find f of x, we're going to have to take the antiderivative of f prime of x. So we'd get 4. The antiderivative of x cubed is x to the 4th divided by 4 plus 3. Antiderivative of x squared is x cubed over 3 minus 4 times, add 1 to the exponent, divide by the same exponent. Now this is some number. So remember what we did up here when we just had some number. We had 4. Well, we said the constant could be written as c times x to the 0. And it's gotten in the way there, so let me write it here. C times x to the 0. So if we add 1 to the exponent, we'd get c times x. But now we would have to add another constant of integration because we found another antiderivative. Now our initial conditions here we can use to find our C and D. So first off, let's use this initial condition here. If x is 0, y is 4. And let me just clean this up before we find our initial conditions. Our f of x equals x to the 4th plus x cubed minus 2x squared plus cx plus d. Now let's use our initial condition. So y equals 4 when x equals 0. So we'd have 0 to the 4th plus 0 cubed minus 2 times 0 squared plus c times 0 plus d. So we're able to conclude here that since this goes to 0, this goes to 0, goes to 0, goes to 0, that d equals 4. So we can plug in 4 for d and then use our second initial condition to find c. So let's plug in d. We have our f of x equals x to the 4th plus x cubed minus 2x squared plus cx plus 4. Now let's use that initial condition. we'd have 1 to the 4th plus 1 cubed minus 2 times 1 squared plus c times 1 plus 4. So here, if we solve for c, we would have 1 equals, we have 1 plus 1 minus 2, so that gives us 0. So we'd have c plus 4, and if we subtracted 4 from both sides, we would get c equals negative 3. So we have our particular solution. So our f of x equals x to the 4th plus x cubed minus 2x squared. Now c we found to be negative 3, so we'd have negative 3x plus 4. And that is our particular solution, because we are able to solve for c and d. This ends part 1 for this section. In part 2, we'll go ahead and look at some problems where we can apply the antiderivative to help us solve those problems.